Okay, let's talk about hypothesis testing with two populations, but specifically we're talking about paired differences now. So dependent samples. Last week we spent the time talking about independent samples, where the samples were not related in any way to each other. And now we're referencing what it means to be a dependent sample, where the two samples taken do have some sort of dependency on each other, and how that changes the hypothesis test. Let's talk about the assumptions, because again, we're in advanced stats now, so the assumptions are something we need to get more and more comfortable with looking for in order for us to handle real data in the real world, and not these preformed paragraphs that make it all nice and pretty in stats textbook. So the first assumption that we need to make is that the sample data is dependent, which means that the experimental units can be paired in such a way they are more alike within the pair than they are within the population as a whole. Now, that doesn't make a whole lot of sense, but when we start doing these examples, I'm hoping that I can really shed some light on this for you and show you why it's paired and considered a dependent sample. The next thing we need to check for is that the matched pairs are simple random sample. That is always the case. We cannot have bias sampling happening like convenience sampling or voluntary response. Third criteria, the number of pairs of sample data is large, larger than 30, that magical number that we learned when we were learning central limit theorem, or the differences are from a population that is normally distributed. So that's a pretty standard assumption that we have to check for. To test the mean difference between two related population means, we treat the difference scores denoted by d sub I as values from a single sample. The general data setup is shown in the table, which will make no sense until we start doing some examples. Okay, in the procedure to do this, we check our samples, which we just ran through, our assumptions rather. And then we need to identify that the mean difference, x bar d, of the samples, mu sub d, which is the population difference, s sub d, which is the difference in standard deviation, and n being the number of pairs of sample data. So because this is paired, the sample sizes for the first sample and the second sample have to be the same, unlike the independent samples where it didn't matter if the first sample had 20 and the second sample had 35. It didn't make a difference, but in a paired data, they do need to be the same. First example, Bull and Bones Brewhouse is a microbrewery. I just had to say it like that. That has two restaurants located within 15 miles of each other. The owner of this brewery wants to compare the average daily food sales of the two restaurants. To do so, the owner randomly selects 10 days over a 5-month period, in college football season, that is, and records the daily food sales. Now, these are considered dependent samples because the sales were collected on the exact same days. If I just chose 10 random sales days for one restaurant and just completely other 10 random days for the other one, those would be independent. They would no longer be linked. The owner wants to know if there's evidence of a difference between the average daily food sales for the two restaurants. Okay, so we have restaurant one, and this chart is continued onto 2 slides because it didn't fit, and restaurant two, and we've also calculated the differences. Now, it doesn't matter whether you subtract restaurant 1 minus 2 or 2 minus 1, as long as you're consistent in your calculations throughout the entire data set. Now, we see that there clearly is a difference. They're not all zeros, but what we want to know is it's a statistically significant difference. In the grand scheme of a day at a restaurant, is $845 difference a big deal? So the data can be paired by day, which is what makes it a dependent sample. Since we only have 10 days worth of data, we first need to determine if it's reasonable to assume that the differences come from a normal population because we do not have sample sizes of 30 or more. We will need to use our guru and our test for normality and our normality plot in order to do this. And we will do that when we switch over to our guru. So for now, I want to make sure we can walk through the setup of the hypothesis before we switch over. So the samples are dependent because they were selected from the same exact days. They are simple random samples because he stated he randomly sampled 10 days out of 5 months. And the differences are approximately normally distributed. We haven't tested for that yet. The publisher is telling us that they tested it. I will show you how to test for that though. So we want to define the null and the alternative. The null will always be that there's no difference, which means the subtraction is equal to 0, while the alternative hypothesis is always going to represent that there is a difference, not equal to 0. In a paired difference experimental design, the population parameter of interest is the population mean of differences. Thus, the appropriate statistical measure is given by mu sub d, the average of the differences in daily sales between two restaurants. Since the owner is interested in whether or not the average daily sales are different between the two restaurants, the alternative hypothesis will be two-sided, and this will be a two-tailed test. The statistical measure being used is the average difference in daily sales between the two restaurants, and we are going to apply our two-tailed test. So our null hypothesis again is that the difference between the two means of the restaurants is 0, meaning there's no difference. And our alternative will say that the difference in the means is not equal to 0, which would mean that there is a significant difference. Okay, now that we have the setup and we have an idea of what we're doing, let's head over to our guru. So I've already copied and pasted the brewery data into an Excel file and then uploaded it into our guru. That Excel file is in this week's content folder, so you'll be able to find that so you can easily upload it. So notice I copied the restaurant 1, restaurant 2, and the differences. So now that we have this uploaded and we double check that it is correctly uploaded, we are going to head over to Analytics. And under Analysis, we are going to select 1 to 2 population mean inference. So mean inference, 1 and 2 population. We are going to select our data set. So for this one, restaurant data. I do need to see the normality plot, and I need it to be tested for normality because we only have 10 data values instead of 30. I'm going to select the first variable to be restaurant 1 and the second to be restaurant 2 to stay consistent with what the PowerPoint was saying, 1 minus 2. So I'll keep it in the same order. Now, when we come down here, we make sure that we select paired. And notice that when it's unselected, it keeps the population separate. But when I select paired, it automatically pairs them and looks at the differences. So we have a sample mean difference, a standard deviation difference, and a sample size of 10. Again, this has to be equal amongst population 1 and population 2. Now let's head over to test the hypothesis 1 to 2 population. Test hypothesis. Our significance level was 0.01. It was listed in there. I didn't emphasize it. Sorry about that. And our alternative is a not equal to sign, and this is always a 0. Now, our sample size is less than 30. We are going to see if it's normal or not when we hit the eyeball, but assuming that it's normal, remember that if it's less than 30, we need to click the t-test statistic because we don't have a population standard deviation and our sample sizes are small. So now I'm going to click my eyeball. Okay, so when I'm looking at this analysis, I see a p-value, and this is for the normality test. So this p-value being very big, we can see that that would mean that we would fail to reject the null hypothesis, which states that the data is normally distributed. And we confirm by the graph that shows that the dots form a linear line and nothing nonlinear. Coming down to the actual hypothesis test with restaurant 1 minus restaurant 2, we see that the p-value is really, really small. Remember, this is scientific notation, 7.8 times 10 to the negative 6, which would move this decimal place to the left 6 places. And therefore, with a very tiny p-value, we are going to reject the null hypothesis, stating that there is not a difference between the restaurant sales, and we would conclude that there is a significant difference between the restaurant sales. So if we take a look, if we were to look at the test statistic and the critical values, which were also listed in that report, we would have the same conclusion. P-value seems to be much quicker for us to conclude. There is sufficient evidence for the owner to conclude that at an alpha level of 0.01, the average daily sales between the two restaurants are significantly different. So if he was caught in a pinch and he needed to close one of his stores, he could be confirmed that one of his stores is doing much better than the other. Our next example, a researcher is interested in knowing the effect which 1 ounce of 100 proof alcohol has on its subjects. To study the effect, the researcher randomly selects 10 subjects and records their reaction times in seconds before and after drinking 1 ounce of 100 proof alcohol. The results of the study are displayed in the next slide. We want to answer the question, can the researcher conclude at a 0.01 alpha level that the average reaction time is no longer after consuming the alcohol than before? Now, this is a paired design because we are using the same 10 subjects for both samples. And in this particular example, it is sufficient to do that because we can test them before and after. So we can see the reaction times in seconds before and the reaction times after. And we want to know if this 1 to 2 second difference is a big deal or is statistically significant. So first, the null hypothesis, there's no difference in the average reaction times. And the alternative is that there is. In paired difference experimental design, the population parameter of interest is the population mean of differences. And therefore, we're using mu sub d. Now, since the researcher is only interested in whether the reaction time is longer after drinking the alcohol, this is a one-sided test. Note from the table that subtracting the after data from the before data would result in a negative difference if the null hypothesis is not true. The statistical measure between used is the average difference in reaction times before and after consuming the alcohol. If the reaction time is longer after the alcohol has been consumed, then the difference will be negative because the reaction time before the alcohol is shorter than the reaction time after. So we are going to set the null hypothesis to the difference between the reaction times to be equal to 0, meaning there is no difference. And we will set our alternative to less than 0 because the average reaction time is higher after drinking the alcohol than before drinking alcohol, which is to be expected. We normally get slower in our reaction time as we drink. But will 1 ounce of 100 proof alcohol make a statistical difference? Let's now head over to Rguroo to compute this. Okay, so I still have the last example up. I'm going to close that out. I'll close the restaurant data. And I have the data I've already input, and that's the before and after times. I can just type these in. This is a very small data set to type in, so it makes sense if we just type in the before and after times by going to Data, Data Import, and create a new data set. Under Analytics, I'm going to go to Analysis. I'm going to compute a mean inference for 2 populations. I'm going to import my data set. Once I find it, here we go, reaction times. This time, I don't remember if it said that it was normally distributed or not, and there's only 10 data values, so I'm going to check it just to make sure. I'll put the before in variable 1 and the after in variable 2, and I'll select paired data so they compute the subtractions. I'll then go over to the population 1 to 2 tab, the test of hypothesis. I'm going to change my significant level to 0.01. And my alternative hypothesis, recall, was a greater than sign because we are trying to show that we have a longer reaction time after the alcohol than before. Again, we're going to have to use a t-test statistic because we don't know the standard deviation of the population, and our sample size is quite small. So our p-value here, 0.035, is larger than 0.01. If we were doing a 0.05 alpha level, then that would be sketchy that this might not actually be normally distributed. But this shows that it is. Although this plot is sketchy, and I'm questioning whether this is actually normally distributed or not. It only works because of 0.01. If this was 0.05, we would say that the p-value is not. We would be rejecting this null that it's normally distributed. But for a p-value of 0.03 compared to an alpha level, we're looking okay. Now, testing the hypothesis paired t-test before and after, our p-value is strong, 0.99945. So with that large of a p-value, we definitely would be failing to reject the null hypothesis and stating that there's no statistical significance between before and after a 100 proof shot of alcohol. Which makes sense. Although one shot of 100 proof, you'll feel that when when you take that, you'll be on fire. It shouldn't affect your reaction time with just one shot, unless you're a lightweight and you have not drinking very much in a very long time, or ever. Okay, so running through these, they checked off approximately normal because, again, with an alpha level of 0.01, it does technically pass, although that's sketchy to me. And we see a p-value. Now, the reason why their p-value is the opposite of our p-value is because they did the subtractant after minus before, and that's why they had a less than sign in their alternative and we had a greater than sign. So if I wanted it to be the same, I would just have to make variable 1 the after and variable 2 the before in our Rguroo. So there's sufficient evidence for the researcher to conclude that the average response time is significantly higher for those subjects who have drunk 1 ounce of 100 proof alcohol than those who have not. Interesting. Because we just calculated the opposite of that and stated that there is, oh, you know what? That's my fault. Because I switched the variables, the conclusion is not the same. Hold on, let me go back through and do it correctly this time. Because we're trying to show that the alcohol causes a longer reaction time, I really do need to go back and switch these two variables because we want the, oh, you know what? I don't need to switch these. I just need to switch this part. Okay, so when we subtract before minus after, if the after is longer, then this should be, we are trying to test that it's negative, that the difference is negative, which is what we were talking about in the PowerPoint. So I have the incorrect symbol, which changes everything for us. So now we have a less than sign here because we're saying if the subtraction is negative, that would indicate that the reaction time after the shot does increase your reaction time. What we tested before was, is our reaction time before the shot longer than that of after? And that was clearly insignificant. No, our reaction time was not longer before the alcohol. So now if we reset, okay, same thing for the normality plot, which to me is a little sketchy because that's really cutting it close. But here's our p-value. That makes more sense. We are rejecting the null hypothesis, and the alternative is going to state that even one shot of 100 proof alcohol will delay our reaction times. Now, we saw in the chart that it's not by a whole lot, it's a second or two. But I guess if you are trying to brake the car, if you happen to be driving while drinking, which I don't advise, you would not be saving that deer that jumped out in front of you. Okay, now let's head over to 8.4 and discuss the inferences about two population proportions. So we've talked about means, but now we want to talk about what it means for proportions. So the sample proportions are from two simple random samples. Okay, that's always going to be the case. Another assumption is that the samples are independent. So for this particular section, we are not talking about paired populations. We're coming back to two completely separate samples. The samples are large enough such that there are at least 10 successes and 10 failures. Okay, so this n times p has to be greater than or equal to 10, and the n times 1 minus p also has to be greater than or equal to 10. In this table, we see the three possible setups. Either the difference between the proportions are equal to 0, indicating no difference, or the difference between the populations are not equal to 0, which means that they're different in some way, or greater than 0, which would indicate that P1's proportion is larger than P2. And here, less than 0 would mean that P2 is larger than P1. Okay, we have our symbols here that we'll be working with, population 1 and population 2. Let's take a look at our first example. A cell phone executive has recently been bombarded with complaints from his customers about defective cell phones. He has two plants that produce these cell phones, and he is not sure where the defective phones are coming from. In the past, the plants have had good control over the number of defective phones produced. Because of the recent flurry of complaints, he thinks that one of the plants may have lost control over its production process. To test this theory, he randomly selects 200 phones from each plant. Notice that there's nothing paired about this. It's just a simple random sample of 200 in the first plant and a simple random sample of 200 phones in the second plant. So they're not paired in any way. The results of the survey are below. So in plant A, 12 out of the 200 were defective, and in plant B, 10 out of the 200 are defective. Our goal is to determine whether there is a meaningful difference between these defective phones. Is there sufficient evidence for the cell phone executive to conclude that there is a difference in proportion of defective cell phones produced by the two plants, with an alpha level quite large at 0.1? So our solution is we're going to let P1 be the plant A and P2 be the plant B proportion of defective phones. And N1 would be the sample size for plant A, and N2 would be the sample size for plant B. Before we can perform a hypothesis test for the difference between population proportions, we need to be sure that the sample sizes are large enough. So remember, that's that n times p and n times 1 minus p. So if we do n, which is 10, no, 200, sorry, 200, and we calculate P1, which, if you recall, proportions are calculated by x over n. So we would have 10 over 200 and 12 over 200, and we'd multiply that by our 200 in order to indicate if we have a large enough sample sizes, which we do. We can indicate approximately normal. Okay, so again, x over n, 12 over 200 gives us a 6% of defective phones. X over n, 10 over 200, 5% of defective phones. Calculating out the n times p and the n times 1 minus p, both of these values, ooh, this one's really close, are 10 or above. So marking off our assumptions, the sample proportions are from simple random samples. They're independent of one another, and they meet the criteria of the central limit theorem. The null hypothesis indicates there's no difference in the proportion of defective phones between the two plants, while the alternative says that there is a difference. Since we don't care which way the difference is, it's a two-tailed test. And we would see that by an equal sign in the null and a not equal sign in the alternative. Let's head over to Rguroo to be able to calculate this example. Okay, let me clear this out because we are not working with this data anymore. And under analytics, I am going to head over to proportion inference of two populations. I don't have a data set for this one. I'm just going to type in the values for this. But what we want to type in is that, let's see. Okay, so our response label we're going to need. A response label is going to be the plants. Our successes is going to be the defective phones. Okay, again, just because it's called a success doesn't mean it's a positive thing. It's just what we're looking for. Let's see. Okay, population 1, we are going to label plant A. And population 2, we'll label plant B. Sample size is 200 across the board. Number of successes, which is X. For plant A, that was 12, and for plant B, that was 10, and the probability of success is calculated automatically. So if you wanted Rguroo to calculate the probability of success for each one of your populations, so you could calculate n times p and n times 1 minus p, you could do that. You could do it from right here. We could be able to calculate those. Now we head over to test of hypothesis. And we are doing an alternative hypothesis not equal to 0. And we are setting our significance level to 0.1. And we're going to hit the eyeball. Ooh, label of population is missing. Oh, well, let's label the population to cell phones. Okay. I missed something. I must have missed something because the hypothesis test is not there. Okay. I'm going to guess that I forgot to select this box. So we need to tell it that we do have a large enough sample and we can use a Z distribution. Much better. So here we go. We have the p-value at 0.66. That's a very large p-value, so we will be failing to reject the null hypothesis, indicating that the proportion of defective phones amongst the two plants is not significantly different. Let's finish up this section. And that is finishing up the section. Let's just look at the conclusion. There is insufficient evidence at a 10% or alpha equals 0.1 for the cell phone executive to conclude that the proportion of defective phones produced differs between the two plants. And that is this week's lessons.